Hi all, welcome back to a boring video about chemistry in open form. Let's talk about some theory today about thermodynamics of particles. We'll begin our discussion with one of the simplest classical models of thermodynamic behavior of gases, the kinetic theory of gases. It's the cornerstone of many principal concepts used in thermodynamics, and according to this theory, molecules can be thought of as these dots or tiny balls that constantly move around in straight lines until they collide with something. Because they are moving, they have energy of motion termed as kinetic energy. They very frequently collide with each other and with the walls of their container. Think of it as a microscopic explanation for the macroscopic behavior of gases. It connects the properties we can easily measure to the unseen world of tiny atoms or molecules that make up the gas. Now, the kinetic theory comes with a few assumptions. The volume occupied by gas particles themselves is considered negligible compared to the total volume of the container they are in. That is, most of the container is empty space. Also, the particles don't attract or repel each other except during very brief moments of collisions. It's assumed that they travel in straight lines between collisions. Also, when particles collide, it's assumed that no kinetic energy is lost, that is, they bounce off perfectly. The energy might be exchanged between particles, but the total kinetic energy remains same. The particles also move in all random directions with a range of speeds. And the most crucial link, it's assumed that the absolute temperature of the gas is directly proportional to the average kinetic energy of its particles. This means that colder gases have particles moving slower and hotter gases have particles moving faster. So this law explains a few properties successfully, like pressure. Pressure is just a result of countless collisions of fast-moving particles with the walls of container. Each collision here exerts a tiny force, and the sum of all the forces exerted by the molecules over the area of the walls is pressure. This law also explains the ideal gas law, where pressure, volume, temperature, and the amount of gas are related based on molecular motion and collisions, the famous PV is equal to nRT equation. And finally, the law also explains diffusion. The random motion of gas particles naturally causes them to spread out and mix with other particles, filling any available volume. Now, this theory does have a few limitations in that it essentially describes an ideal gas, not a real gas. Wait, what's an ideal gas and what's a real gas? It's the exact same difference between real money and fake money. It looks pretty but not really useful for anything meaningful. An ideal gas is one that is assumed for this theory, that is, particles with no volume of their own, no intermolecular forces, etc. A real gas, of course, has particles with finite volumes and they do experience intermolecular forces, leading to deviations from quote-unquote ideal behavior. This is much more prevalent at high pressures or low temperatures. High pressures, particles are forced closer together, which leads to their volume becoming significant compared to the container volume. Low temperatures, the particles move slower, so the weak intermolecular attractive forces become more important and can't be ignored. Now, this helps explain why a more robust or a real gas model is required. These models help add corrections to the ideal gas law to account for particle volume and intermolecular forces. Also, this law helps explain what viscosity is. Viscosity is the property of fluids, which explains why some fluids tend to flow slower, but others can flow faster. What we can see here is the top wall moving to the right at a certain fixed velocity. We can observe the movement of particles along the wall, which elucidates why fluid particles in close proximity to the wall adhere to the moving surface. We could see some particles sticking together, forming rotating structures. Keep in mind that this is a simple Python script trying its best to do what I told it to do, that is, have dots move around in a space bound by a rectangular box with some physics attached to it. This is in no way a true representation of how fluid particles may behave, since this lacks the intermolecular forces. But this nails the point of kinetic theory and helps explain the concept of viscosity, so I'll take it. As the wall velocity increases, the fluid still forms eddies and tries to move particles away from the wall, transferring energy in layers. Now, this law also helps explain thermal conductivity. In essence, conductivity is the ability of these particles to transfer kinetic energy between each other. It's a bit more complicated, but for the purposes of the theory, let's assume that. We can see the dots here varying from blue, low temperature, to red, high temperature, situated in a box with a red wall on the left, which is in, again, high temperature, and a blue wall on the right with low temperature. Notice how the dots gain speed once they hit this red wall, but slow down when they hit the blue wall. This helps explain the point about thermal conductivity, where a fast-moving particle travels into the bulk of fluid, and as it collides with the slower-moving particles, the kinetic energy is transferred, and this process just cascades. We see energy flowing from hot side to the cold side via these chains of collisions. Now here we talk about the high thermal conductivity, where essentially the energy transfer per collision is efficient. We can see that the temperature gradient, so to speak, is shallower and more uniform across the box. This essentially means that the particles are able to transfer the kinetic energy easily. We could also see here the flow of temperature, where particles are trying to move to the right or from hot side to cold side as much as possible. Now on the opposite end of the spectrum, we have low thermal conductivity, which in a sense means that the energy transfer per collision is quite inefficient, or the temperature gradient is steeper near the hot wall, with most of the fluid remaining cold even after enough time has passed. Now these animations do lack some interesting physics of molecular forces of attraction or repulsion, but it helps explain the concepts through interesting methods. I will provide the Python codes of these animations I've used in the link in the description through my GitHub. You can find them there and play around with these. Now, moving on. So, of course, real-world scenarios warrant better models to explain the behavior of gases at different states. For example, cases where gas pressure is high or temperature is low. The kinetic theory fails. More complex models like the real gas equation of state or something like the Sutherland Model exist to solve this exact problem. Let's talk about this gentleman, William Sutherland. Look how dapper he dresses. His paper from 1893 helps address the problems faced by the kinetic theory. He talks about how the kinetic theory treats molecules as simple hard spheres that only interact during collisions. Also, that gas viscosity is independent of pressure, and according to this theory, viscosity should be proportional to square root of absolute temperature, whereas experiments clearly showed that viscosity increased faster than root of t, and it suggested that it must be t to the power n, where n can be anywhere between 0.7 and 1.0. His core findings explain that molecular attraction matters and collision probability should be way more than predicted earlier. He also proved the temperature dependence of the effect between low temperature and high temperature. Sutherland argued that the effect of molecular attraction is equivalent to making the molecules behave as if they were large spheres when it comes to calculating collision rates. He incorporates this temperature-dependent effective collision area into the standard kinetic theory formula. Also, he took high-quality experimental data for the variation of viscosity with temperature for air and carbon dioxide, where he tuned the constant C required to fit the data at different temperature intervals. Remember this point, it becomes relevant later. He demonstrated that the consistency of C with independent estimates of molecular size, intermolecular forces from equation of state studies, and thermal conductivity data. The link to the paper, you can find it in the description. So, we find that viscosity, density, and something called the specific heat are related to temperature. Specific heat is exactly what you think it is. It is heat required to raise the temperature of a substance by 1 degree Celsius or Kelvin. These properties are quite dependent on temperature, varying the bulk fluid flow, and as is with CFD, this cannot be estimated for every single degree change in temperature, but rather warrants that we use models that can be evaluated on the fly. This has a profound effect on the accuracy of your results. In essence, we use certain correlation models or equations to solve for these properties. These are tried and tested methods that work within certain ranges or a particular type of problem. It's necessary to read about the models before implementing them. I would not be able to cover all these models. However, I would be pointing out the major models that we should be using in our journey with combustion in OpenFOAM. All of these models are specified in a file called thermo-physical properties in OpenFOAM. It is to be placed in the constant folder of your directory.